So hello everyone, welcome to our talk here at EclipseCon. It's my pleasure to be together with Frédéric, and together we are going to talk about open source hardware. So this is the agenda of today. I'll give a brief introduction of OpenHW Group, where it is, who we are, our products, so the CORE-V family, and then Frédéric will show a demo showing one of our MCU. And finally, we give a conclusion. So we are quite active here at EclipseCon. Here you see, today there's me with Frédéric. And then tomorrow we will have plenty of other talks. We have Rick here at 10:45. Then we have Intel together with another member of our staff at 2:30. Then another talk at 4 from Thales. And then eventually we conclude with a bird of feather at 7 p.m. So what is OpenHW Group? OpenHW Group is a non-for-profit global organization. So we are present globally with the legal entities in Canada. And what we do is doing open source hardware at industrial grade. This is in short. As today, our main products are based on RISC-V, so we do processors based on open source instruction set architecture. And we are member driven, so maybe this thing sounds familiar for those who already know how Eclipse works. We have more than 96 members. Here you see the major ones from the industrial domain, but we also have academic members and partners that help us curating the ecosystem. So in short, what we do is creating, maintaining, and populating open source. We use GitHub and GitLab, industrial grade IPs. So they are we have plenty of IPs that are released with permissive licenses based on the Apache v2 for what concerns the software and the solder pad for what concerns the hardware. Then we are here helping people knowing what we do, so communication. And what we also do is coordinating our members and other supporters for working all together on common projects and common goals. The way we are structured is via working groups and task groups. We have a board of directors, then we have the technical working group that curates the technical part of our ecosystem, which is split done by core, verification, software, and hardware task groups. So this is to focus more on technical activities. And then we have a marketing working group, but also, which is what I'm going to talk about shortly, we also have working groups that are curating the regional aspects of OpenHW Group. So OpenHW is global organizations, but we need the lens to focus more on regional aspects for what concerns, for example, Asia and Europe. So in this slide, I'll show you what Eclipse, together with OpenHW, built for what concerns the European working group. So we created a working group within Eclipse called OpenHW Europe. This is basically a close collaboration between the two foundations that will basically focus on the European needs and complete the OpenHW activities from the European side. Let me give you some examples. So we have, for example, activities within the OpenHW Europe that focus on the digital technology, digital sovereignty, the requirements from a strategic, technical, and marketing point of view. And also, by having an European-only working group, we, let's say, close the collaboration among European members that can have, the same time zone, the same physical place to meet up, and so on. And we also can participate via Eclipse then, because now the European Europe working group is within Eclipse, so it is a European entity. We can participate to European projects. For example, the Tristan is the one we recently participate in, that we are starting. It's a KDT lasting for 3 years. And this project is basically focusing on strategic autonomy in the electronics market for the European Union. And what OpenHW Europe does is giving open source hardware standards, so to curate the IPs at industrial level, and implementing together with Eclipse digital sovereignty. So this is the roadmap of our IPs. So now I'm switching to the open hardware at large IPs. So those are all the RISC-V CPUs. We have both in the application domain, so capable of running Linux, and in the embedded domain, so the one meant for low power and real-time applications. So we have different cores. I try to group them in families. We have the 4th stage, so the 4 stands for the number of stages. In the embedded domain, CVE4, those are in order single issue cores, which have a baseline ISA based on RISC-V, which implements the IMC. And then we have, for example, the E40P, which is the pulp core, for those who are familiar with, which is a CPU extended with custom extension to have efficiency on DSP and SIMD applications. Then we have the E40X, which is customizable, so as the E40P, but the 40P has a, let's say, a given extensions, whereas the E40X is extendable without the CPU knowing what the extensions are. And then the E40S, that is the core meant to run security applications with custom extensions in the security, side channel attack supports, and so on. Then we have the smallest low-cost core. This is only 2 stages, so performance are also compromised, and those CPUs are meant to run finite state machines, control applications, where performance is not really a big requirement, but rather low power and area, in always-on applications, for example. And then, moving up, we have the CVA6. This was known as Ariane from Zurich, from the ETH Zurich, and is an application class core. So this guy has the full support of memory managed units, protection memories, caches, TLB, and all those ingredients are help running operating systems such as Linux. Actually, this CPU runs Linux. We have both the 64 and 32-bit support. 64 for let's say, big applications, and 32 for, let's say, the smaller version, the smallest being without floating point, MMU, caches, and so on. And then we also have a soft core. This is meant to be implemented on FPGAs, which is an application class 5-stage core, CVA5, based on the Taiga core. And this is, for example, capable of running instructions in an out-of-order fashion and being efficient on those applications that leverages it. Then we also have an MCU, and Frédéric will show you an application running on top. This is a full microcontroller, so we not only have the CPU, but also a platform of peripherals, memories, DMA, an embedded FPGA to customize the CPU post-silicons, and so on. We target the tape out beginning next year in 22 nanometers, FDSOI, and we will have the 32E40P core, which is the first one that achieved technology readiness level 5, so fully verified. But also to help the software, and the team is actually based on development, we also have an emulation platform, so the implementation of the MCU that I just showed on an FPGA. And now I leave to Frédéric the description of the demo.
Yeah, so I have the chance to work with my friend here on this, and it's been instructional. I mean, when you think about it, open source has been transformative for software, and the thought that now we can do it in hardware as well is really a game changer from my perspective. In IoT and Edge, you want to customize what you deploy in the field to absolutely push to the limit your your power consumption, keep it as low as possible, optimize bandwidth usage and things like that. And by having, of course, open source hardware, you can achieve those things in a more efficient manner because you can cut the features that you don't need or implement existing features in a better way. So in this particular demo, unfortunately, we don't have the actual MCU since, well, it seems there are delays at the foundry, so we are using the FPGA platform. So in a way, we're doing what the guys at Open Hardware are doing in order to create the chip, right? They write this system Verilog stuff that you can find on GitHub, and then using a set of tools, you can put that on a USB stick and run that on the FPGA board that we've got here. So in this particular demo, I'm running the CORE-V IDE built on the Eclipse CDT tools, okay? And we, through the little debug probe from Ashling, deploy our FreeRTOS application to the FPGA board. So the FPGA board itself is initialized with the CORE-V MCU, so that's why you see a USB stick, well, not on the photo, but sticking from the one on the desk. So the USB stick contains what they call the bit stream, so that's the compiled version of the MCU, let's say, that you put on the FPGA to run it, and then I deploy my FreeRTOS application on the top of that. And I capture the output of the application through serial port, well, emulation on USB in this case. And I have a little Python program that waits for those messages and sends that to the Mosquito broker, and we display the output in the Stream Sheets platform since, well, it's a bit nicer than have text output, just for the sake of it, and show how comprehensive our ecosystem of open source hardware plus software is. So from a code point, I mean, the code is quite simple. There's nothing special in there, so just putting, you know, a few lines there. So that's from the FreeRTOS application. So you see that I do a read on the temp sensor. So there's a temperature sensor on the FPGA that we're using for that over the I2C connection. And so that's a plain read. And then we do a little niftily printed output on the console. And then I format it as JSON as well, and my little Python program considers everything in JSON is output that we need to send on MQTT. So, of course, that's not production-ready design or anything, but it's a nice way to do it. And from the Python side, connecting to the MQTT broker is very easy. We are using the PAHO MQTT client there, so nothing special there. And then we connect to the serial port. And well, one little interesting detail is that I had assumed that the defaults would be fine to connect to it, but I had to set the baud rate to the correct rate in order for things to work. If I was using a lower value than that, the output was all scrambled. You wouldn't expect that. It's over USB, so it's fast enough. And no, you have to take into account. So, you know, I was reliving my days of youth when I had air and a Hayes smart modem on my desk. Anyway, so essentially the code there is quite simple. We just capture any line that starts, you know, as a JSON output and send that on a specific topic on the MQTT broker, and that's it. So the program overall, it's full of comments and all of that, but it's about 60 lines, so nothing really complicated. So now, let's see that in action and see if I can break things or not. Because, of course, this is not a real demo if it works. Or not, we'll see. All right, so this is a CORE-V IDE in dark mode on Linux. So at this point in time, the CORE-V SDK is available on Linux and Windows. But in the case of Linux, don't make the mistake I did. You need Ubuntu 20.04. Nothing else. Okay, 22? No, won't work. Older than that? No. So 20.04. And believe me, you have no ideas how many times, you know, I reflashed my laptop because I didn't have the right combinations and I wanted to run something else. And so running 2 Linux distros in dual boot mode, in secure boot mode on the laptop is hell on earth. I did all of that for you. Okay. So we see here the CORE-V IDE, but right now I have nothing running. So let me unplug everything and show you how I would, you know, run all of this. So right now, my little board is not powered, so the first step is really to plug one cable for the debug probe. So this is a very nice probe. It supports ARM-based, RISC-V, and I think other things as well. Anyway, it's a nice little product if you need a separate probe for a board that doesn't have it. And the first step is really to plug the USB for my little FPGA so that it will initialize. So when I do that, it reads the bit stream from the USB stick, and so it puts the MCU, so to speak, on the chip. Now, in terms of performance, I was curious, Rick, do we have roughly the same level of performance as the actual MCU, or is it lower because of the capabilities of the MCU, the FPGA?
Hardware emulation, we don't care what the clock speed is in the FPGA.
Mm-hmm.
It's just to validate the logic.
Yeah, so I shouldn't expect any type of...
Clock speed is, I think, 50 meg or 40 meg, something like that.
Yeah, okay.
The MCU itself will be 300 or 350 or something.
All right. So at this point in time, my little FPGA is running, so that's the wrong window, and we will have a look at what's happening, you know, just in the terminal. So we see here, boot me, boot me, boot me. So that's literally the signal that I have my MCU running on the FPGA, but it's not executing any application at this point in time. Okay, and when I say terminal for the younger crowd maybe, so this is not the terminal application, but this is a modem terminal application running over the serial port, of course. Okay, so let me exit that. And so the next step is really to deploy my FreeRTOS application on there. Okay, so I will start the debug right here. And so it compiles and it deploys using the debug probe. And now we see at this point very shortly that it will be running. And so I need, come on, yeah, getting there. All right, so now it's running. I just need to resume execution. And at this point, okay, I have my little program iterating, making temperature readings, and generally having a good time, I hope. So what I will do next is start my little Python program, okay? And of course, you know, this is really professional. You know, I have a little banner and everything, given that we are doing this for real right now. Security always gets in the way. All right, come on. It will be better with the full password. Okay, so it will take some time because, of course, it's not. You know, I put a very leisurely timeout in there. Okay, so the location is wrong. You know, I didn't take the time to fix this or anything. But in any case, we see okay the pretty printed version and then the JSON version, and the message has been successfully published on our MQTT server. Now, in the interest of time, you know, I could go text mode and all of that and show you that it's, by subscribing, that it's actually there on the broker, but we'll go straight to Stream Sheets. So Stream Sheets is running in Docker on my machine. So you see here the kind of welcome page, and you see that I have a Core-V Stream Sheet here. So for those of you who don't know Stream Sheets, it's a platform where essentially you can put a spreadsheet-like interface on the top of IoT data streams. So it supports MQTT, OPC UA, and many other protocols. So in this case, I just connect to the same broker that my little Python program is connected to. And when it will load the sheet, by default, it's not running. So we see the data from the last time that I ran it. So you see the ID of the place, the temperature. And in this case, I also added the MQTT ID for the message so that we can distinguish, you know, the various readings in there. So when I click on, you know, Start App, it will start monitoring in real time the MQTT topic, and we see it changing right now. So that's the current reading. I could ask one of you to blow some air on the temperature sensor, maybe to change the value, whatever. So we see the ID changing, so we are getting those regular readings from the little application. And this is literally an end-to-end open source solution for IoT and or edge, in action in front of your eyes. So nothing special, nothing fancy, but at the same time, it's quite exciting to think that I've got this programmable chip here, and I was able to deploy the Core-V MCU and everything, and my own program on the top of that. All right, so very briefly now to complete the presentation, now that, well, of course, this demo is completely staged and fake because it didn't crash. No, it's an actual thing, and of course we'll make somehow the code available for the little Python program if you are interested, and my little modifications to the samples that OpenHW provide for the FreeRTOS app. Anyway, so to really complete this presentation, what I want to impress on you is that the Eclipse Foundation, OpenHW Group are really, kind of sister organizations. We have very, tight back office ties on the top of everything that we do together. And what we are building is this comprehensive ecosystem all the way from open source hardware to IoT platforms at the top. And of course, as time passes, we will try to incite more and more Eclipse IoT projects to make sure that their stuff works well with Core-V processors and boards and things like that. And really, in our case, from the Eclipse perspective, all of this is happening in the Eclipse IoT working group, so a great bunch of people that care pretty much about IoT. And of course, we are always looking for more, so let me know if you are interested. And all of that, when you position this in a reference, kind of reference IoT and edge architecture like this, you see how comprehensive the toolkit is. So I showed you stream sheets, which is just a little part, but there are so many things available in there. And of course, all of that on the foundation of open source hardware. This is really the stepping stone for everything else in due time. I'm looking forward to be able to have a little gateway with the CVS6 and all of that. So we are just getting started, but really already what we can accomplish there is quite impressive. And that's about it. So thank you so much for being here. I suppose we have some time for questions. I'm not sure how tight we are on time, but in any case, thank you so much for being here today. So, any questions? Was that so clear that you don't have any questions? Yes.
I'm Leonardo from the Space Lab, so I'm in the space industry. We are also interested in RISC-V architecture in space. But the challenge in space is to verify the scalability of tasks running into an operating system. You have tooling that are able to do that.
Do you have?
Tooling.
Tooling.
The tasks, deadlines.
That will be more in the software side, right? Well, usually, I guess, which operating system do you usually run on edge devices to do that?
In the space industry, we are running Spark V8 architecture, so it's a very old architecture, and we have our own tool to verify the scalability of the system. But it would be interesting if you have such tools to verify the deadlines of all the activities running into those kind of processes.
The secure core that I presented, so the CV32E40P, is actually meant to be secured, and there's some overlap with actually your applications, because that core try to have the same latency for each instruction. So that will, I'm not sure if it will make it formally predictable, but it's the most predictable core we have as today. Then on top of that, if that is the case, you could actually then deploy your operating systems of applications. In case they are meant for Spark, I think it's an application class. But if you have a real-time operating system running on top, then ported maybe to RISC-V. And I'm not very, let's say, aware of space applications and not don't know enough to give you a yes/no answer. But that's on top of my head what I will look for the solutions.
Also, one question. So, I'm Frédéric. I'm involved with the CP for Cloud project. What I'm interested in is if somebody wants to get a feedback with open hardware, do you, is there some reference board that you point people to, okay, order this and you can start developing hardware? Is there something which you can recommend?
Sure.
You want, yeah.
Yeah, sure. I mean, that board, the FPGA board that's sitting there is a Digilent FPGA Nexus A7 board. You get the FPGA board, download the bitstream. You've got the MCU running that Frédéric has in the demo. Connect to it and beat it up. Yeah, it's for that FPGA board, like $300, I think, something like that. So that depends on who you are and where you live, according to Digilent, and I don't make up the price. It's not our board or anything, right? It's from Digilent, a rather prominent FPGA board supplier. You can get them from DigiKey, and any major distributor carries those boards.
And Rick, you will have the evaluation boards for the MCU 2023, right?
Right. So what Frédéric's talking about is we're taping out that MCU in GlobalFoundries 22FDX and building a development kit. We haven't landed on the exact pricing. It'll be less than the FPGA board for sure. And then you don't need to go through the hassle of downloading a bitstream and anything. It's a little MCU that just runs basically the exact same development environment that's on that FPGA board. And we should get silicon back from Global. Crossing my fingers here. We've been waiting anyway.
I was hoping for Christmas.
Yeah, so was I. We were hoping we were going to get silicon in Q4 this quarter, but that's not the case. So first half of next year, we should have some boards back.
Well, thank you again. Have a fantastic EclipseCon.